to use them interchangeably. They both mean the mean. And sometimes you'll see x bar, that's on your calculator, and sometimes you'll see mu, which is in all the formulas you're going to get. Because the formulas that we're using in this class are all for the populations. There's different formulas for some of these things we're going to be looking at if you have a sample. For our purposes, we're not worrying about sample formulas. We're only worrying about population ones that have mu's in them. This may make not a lot of sense just yet, but when we start looking at the formulas, hopefully that'll make more sense. So I'm going to start using mu a lot when I'm talking about mu. And again, if you forget, what's the figure making? Just ask me in case it kind of is slipping your mind. But that little funny looking M is a mu, and that means mean. Now we're looking at measures of spread variability now, not at just those measures of central tendency. And we know some. What's range again?
The
Right, the biggest one is the smallest. Using the words that we used for the box and whisker, upper extreme minus the lower extreme. If you were using the calculator, it said max x minus min x. That's how you get the range. The biggest value minus the smallest value. Interquartile range, what was that again?
How big the box?
How long that box is in a box and whisker. That's the upper quartile minus the lower quartile. In your calculator, we say Q3 minus Q1. So it's the length of a box and whiskers. Now think about what I mean by spread. So if your grades, we had an example last time, somebody had a 48 and a 100. So what's that range? What's the spread from that based on range? 52. 50, 100 minus 48, right? So that number said, wow, that's a big gap. If somebody had like 100 and a 90, their biggest grade was 100, their smallest one was a 90, what's their spread or range? 10. So does that tell us something about the data? Does it? So if somebody has a range on their grades of, what did I say, 52? And somebody has 10. That's their range of their numbers. Does that give you any information about their grades at all? No? Now, I don't know specifically what their grades are. Do I know anything about the numbers themselves in there? Do I know if I have a big range and somewhere I've got a big number and somewhere I've got a small number? And if this is a kind of a smallish number, they're not that far apart. So this is kind of what we're getting at. Looking at variability, how can I tell if my numbers are alike or if my numbers are different? In this case, the numbers are really different, some of them. And in this case, they're less different because of range. Well, we're going to look at other measures of spread. And we're going to look at this idea of average distance from the mean. That's kind of a new idea. So we're going to do an example here. Because I think these words don't help us much. Tell us how far from the middle on average. Each point of data set is from the mean. Does that mean anything to anybody? Anybody? No? Yeah. Let's look at an example. So here's an example of, and this is not the note, so this is like if you want to write it down, just to get an idea of what's going on here. So I took the ages of children in a family. These are 5 children in a family. This is how old they are. And I want to find the average length from the mean age. All right, so what am I doing? First of all, I want to find the average length from the mean age. So I have to find the mean. So let's just review on the calculator how you can use the calculator to find the mean. I got some stuff in here, so I'm going to empty it out. You know, I want most of that data. So anyway, I want to find the mean. So let's see. How old are the children? I have a 10-year-old, 11, 14, 15, and 20, right? Those are my ages of my children. So I do a stat, I calc, one variable statistics. I can put the O one in or I can leave it out. So what is my average age? What is my mean? And I wrote mu on the, I wrote mu up here. Well, what does it say up there? X bar, right? So they mean the same thing. And what is it? 14. So the average age of the children here, for me, is 14. And now what I'm going to do is I want to figure out how far away each age is from the mean. And what do I mean by that? So these are my ages. 10, 11, 14, 15, and 20. I want to find out how far away. So let's look at the 10-year-old, right? The mean is 14. How far away is the 10-year-old So if I call these my x's, and I'm going to call my data points x, how did I get there? I took the x and I subtracted the mean. I said, what's the data point? And I subtracted mean. Right? Say yes. Yes, good. We call this, has a special name. In statistics, we call that value, just call it a deviation. Meaning, how far is it from the mean? So x minus mean is we just call it a deviation. But this is what they are, right? So if I want to find the average that it's away from the mean, can I just average these numbers? Wouldn't that be averaging how far away they are? So let's do that. So I'm getting negative 4 plus negative 3. Now do I have to add that 0 in? Yeah, I put the 0 in, right? I'm just averaging these numbers. What am I going to divide by? 5. Why am I dividing by 5? Because there's 5 things. And if you remember, we saw it on the calculator. We used the symbol n to stand for the number of data points. So in this case, my n equals 5, so I divide by it. Let's see what I get. Negative 4 plus negative 3. Negative 7 plus 0. Negative 7 plus 1. Negative 6 plus 6. 0 over 5, which is 0. What? 0 over 5. 0. Wait a second. So this says that the average distance, or how far away they are from the mean, is 0? That means, wouldn't that mean everybody's 14? What's going on? Why did I get 0? That doesn't make a whole lot of sense. How did I get the 0? Let's think about this. I tried to draw this little graphic picture here. This line represents a mean age of 14, right? That's my mean. Now this child here, this 10-year-old, isn't he 4 under? No, we said the 11-year-old, he's 3 years less than being 14. Well, he's right at 14, he's in 0. He's 1 year older, he's 6 years older. Well, what's going on here? Why are these below and these above? They appear to balance out, right? This one's negative 4, negative 7. 6, 4, that's positive 7. They're canceling each other out. What's going on? Well, why is that happening? Well, wait for me to tell you. I want you to tell me. What do I know about a mean? What is a mean? What is a mean? I want more like kind of words explaining what a mean is. I don't want the formula. Well, what is it? It's a what? It's a balance point. What do you mean by that? Right. What do you mean by that? It's the middle. It's the middle, and we calculated this middle, right? It's not a median. We calculated this middle to be the middle, the exact middle. You're in the middle. Aren't they the same number above as below? So isn't this true for every mean? You're going to have the same number of points either above it or below it. Yes? So is this going to happen for any data set? Any data set where I say, how far away are you from the mean? Are they going to balance out like that? Is the mean always the balance point? Yeah, this is a problem. Because this is not helping you find average distance from the mean. So what we do instead is we want to find a better way to deal with these values. We're going to use distance instead of the how far above or how far below. Because distance is always positive, isn't it? Is distance always positive? Think about it. Do I say, I live -3 miles from school? No, we don't say that. Distance is a magnitude. It's a value to describe how many miles. 3 miles. I don't care which direction. I'm 3 miles away. So it's always positive. So how can I take some negative number and turn it positive? What's that thing? She's making the bars. What do we call those bars? The absolute value. So remember what we did. We took this x minus the mean. Remember, those are called deviations. Now I'm going to put absolute value bars around them. So now I'm asking, he's 4 under, but using a magnitude of distance. What's the distance to 14? 4. What's the distance for this 11-year-old? 3. The 14-year-old still 0. The distance from 14 is 1 and 6. Now I have go to a decimal here. And plus, you know, it is a real life situation. These are ages of children. It's a real life situation. Most of us can't think of, oh, this one's about 14 kids away. So tell me approximately to the nearest tenth, what is 14 over 5? You got calculators? Yeah. It's about 2.8. You know what? I'm going to take it one better. For this example, I'm going to say it's approximately 3 for this example here. So what does this mean? I'm getting this number 3. Now we're going to go to a second. So we're going to just finish this one thought. The mean is 14. The average distance from the mean is approximately 3. How do we interpret this number? On average, each child is 3 years from the mean age. If my mean is 14, on average, each child, now is each child 3 years away? No. But the average age from that mean is 3. And we're going to talk about it when we come back from lunch, what we mean by that, why that might be. So on average, each child is 3 years away from the mean. Now let's think about what that's telling us. Excuse me. So each child, 3 is 3 away. What does that mean? Now let's say there's another family, a whole other family with a whole other set of kids, and I do the same exercise. I find out the mean of the ages of the kids. I find out the absolute value, the distance of how far away they are from the mean, and I come up with 5. Right, this one was 3 years away, and another family was 5 years away. Is that telling me anything? Is that information useful in any way? Is there anything that this tells me? What do you think? It's telling me the kids are more spread apart. How come? Because if they're 3 years on average, 3 years away, that means they're all pretty close to the mean, or at least they're within 3 years, most of them on average. Whereas they're like 5 years away. So that means that this one is more spread apart. The ages are more spread apart. There's like a much older ones, a much younger ones. If you look at these numbers here, apart from maybe the 20, they're all kind of pretty close in age. So these numbers are helping tell us something about the data. And let's see if we can kind of think about it a little bit more, which is, I just added a 0 age. What does that mean? Less events. Look, look. Aww. Right? They had a baby. They had aw, six kids. Anybody here a big family? 6 kids? No, I do. 2. Okay. I'm feeling for them. But anyway, so they've got 6 kids now. So what's that going to do? Right? Before, let's remember what the numbers was. We had a mu of 14. Our average was 14, and we found that on average they were 3 years away from the mean, right? So now it's going to happen. 3 is our outlier. Well, it's an extreme, but let's see what happens. So now I have to find a new mean. So I'm going to use my calculator, hopefully. I'm going to go back to my list. I think they're still in there. So now I'm going to add the baby. Here it is. So now I have the baby in the list. When I do my stat, my calc, my one variable statistics on list 1, I'm going to get a new mean. And what's my new mean? Right, we're little correct bar here. About 12, right? Let's say it's 11.666, 11.7. Let's go with 12 to make this a little bit easier. So why did my mean go down? Why did the mean go down? Yeah, because this new baby is 0, that's going to bring it down. Because remember, that's not going to change the so many, but now I'm dividing by what? What's my new n? 6, right? Now there's 6 kids. So we're going to get a lower mean. So what does that do for our numbers? So this child was a baby. He's 0. He's 12 years below the mean. We're going to use 12 to say he's 12 years away from the mean. This kid who's 10, now he's 2 years away from the mean. This child who is 11 is 1 year away. Even though he's 1 under, we're just going to say he's 1 away. My 14-year-old is no longer the average age. He's now 2 above. The 15-year-old is 3 above. And the 20-year-old is 8 above. So let's see if we can figure out from the average from this. So we're going to add 12 plus 2 plus 1, plus 2, plus 3, plus 8. Right? These are my new distances from the mean. And if I divide by my n of 6, I should get my new average distance from the mean. What do we get here? 12 plus 2 is 14, plus 1 is 15, 17, plus 3, 28. All over 6. Calculate, friends. What is that to, I don't know, there's 10. What is it? 4.6, so approximately 5. So now we went from being 3 years away to being 5 years away in terms of average. So let's see, before the baby, our mean was 14, and our average distance was 3. After the baby, our mean is 12, and our average distance from the mean is 5. So what does this tell us about the data here? And what information does the average distance from the mean give us that the mean itself doesn't? Right? So the mean, this mean age is 14, mean is 12, so what? But what does this number help us learn about these groups? And I think you gave me the answer before. Think about the spread of the ages. If somebody has a 3-year average distance from the mean and somebody has a 5-year average distance from the mean, what does that tell us about the data itself? What? Looking at this one and looking at this one, right? These are the average distances from the mean. This one's a 3, this one's a 5. Does it tell me anything or is it worthless? You told me before. What does it tell us? They're more spread out. These are more spread out. And aren't they? We have a baby of 0. So the bigger this number is, the more spread out your data is, the smaller it is, the less spread out. And so by spread out, what does that mean? These numbers are more alike. Meaning compared to each other. And these numbers are more different compared to each other. Because we now have wider age spreads once that baby came into play here. So a small average distance from the mean indicates the data is close together, and a large average distance from the mean indicates the data is farther apart. So let's look at this example here. The average distance from the mean of heights for one basketball team is 5. Average distance from the mean. The average distance from the mean for another basketball team is 10. So this basketball team has an average distance from the mean of 5. This one has an average distance from the mean of 10. Which team has players that have more similar heights than the other? Why 5? Because it's smaller. Say it again. Say it nice and loud. Smaller. There's a smaller average distance from the mean, so the numbers must be closer together. This has a bigger average distance from the mean, so the heights of the ball players have to be more different. See that or not see that? Raise your hand. I don't know what you mean. Raise your hand. I do know what you mean. Okay, you have to pick one or the other. I get it. I don't get it. There's thumb up, middle, down. Now, if you're middle, you have to ask me a question. Where am I losing it? Oh, so no, I'm really thumb up. I'm fine now. No, because really, if you're not getting it, you got to talk to me. Right? On average, how far is each player from their mean height? Do I know what the mean height is? Do I know how tall they are? I have no idea. But on average, they're 5 years from the mean. On average, they're 10 years from the mean. Like if you think, I don't know what the mean is, but on average, each player is about 5 away. On average, each one's about 10 away. So which ones have players that are all kind of close to the average? Which one has players that are all kind of close to the average? This one. If they're all close to the average, they're all pretty close to being the same. Yeah. Well, does that make sense? Right? What does this number mean? On average, the players are 5, I didn't say what the units are, 5 inches from being in the mean. Right? So maybe they're 5 inches away from whatever that mean height is. I don't know what it is. But on this one, on average, they're about 10 away. So think about that. I've got all kinds of heights going on here. Or maybe I've got 1 or 2 real extreme heights. Yum doesn't play anymore. I don't know who's the tallest player in the league these days. I don't know. Do we know that? No? We don't have basketball league? Come on. You don't love basketball? Oh. You should do that as your homework assignment. But, maybe that guy's on his team. What? We used to have Manu Cole, right? He was really, really tall, and Yao Ming was really, really tall. I don't know who the really, really tall guy is anymore. They're both done. I don't know. But that's what's going on here. All right. Dewey? What's all of it? 7 something? Well, maybe he's over here. Oh. No, he got by this tall. Oh, I don't know. I don't know basketball at all, by the way. I don't know if you noticed. So anyway, this is the big idea. If the average distance from the mean is small, the numbers are close together. If the average distance from the mean is big, then the numbers are farther apart. There's a bigger spread between them. Now, this thing that we've been doing all along, it has a name. This average distance from the mean that we've been finding is called mean absolute deviation. And we abbreviate it to MAD. Mean absolute deviation. We find it, now I like the name of it because it really tells you how to find it. We find it by finding the mean, right, of the absolute value of the deviations. Now we talked a little bit about a deviation, x minus mean. You take each data point and subtract the mean. You take its absolute value. Once you've done that, you find the mean of all of those. That's what we've been doing. So we have a little bit more for that. The quantity x minus mu, that's called a deviation. And it measures how far above or below the mean of a data point is. A deviation can be positive or it can be negative. Think of when that kid was 4 years under the mean. So he had a deviation of -4 because he was 10 years old and the mean was 14. Now what we do is we take the absolute value of these deviations and then we take the mean of all of them. That's what we were doing. Okay? So we take the sum of the absolute value of the deviations and divide by the number of data points. Isn't adding stuff and dividing by the number of data points a mean? So the MAD is a mean, and it's the mean of these absolute value of the deviations. Now I'm going to write it like this now. N, as we recall, that's always the number of data points. And our calculator calls it the same thing, because that's a statistics thing. We call our mean mu. Each data point is called x. Even though I've got a bunch of them, they're all x. So a data point minus the mean, take the absolute value, add them together, and divide by the number you have. That's how you find mean absolute deviation. So that's the formula for it. So let's try it. If you look on the bottom of page 2, and we're on your notes now, the bottom of page 2, we all find it. Bottom of page 2. Right place. Wrong place. Right, that's page 2. Right? Bottom of page 2. Yeah. Bottom of page 2. Okay. So I want to find the mean absolute deviation of this set of points. Alright, so what do I have to do first? Well, look at this. I'm giving you the mean. I'm giving it to you. So remember, maybe in years past, finding it may have been your goal. Now we're assuming, well, it's easy to find. You can just plug these numbers in the calculator and find it. So that's not our goal here. We're going to be using this mean. How did I get n equals 6? Where'd that come from? The number of numbers. 1, 2, 3, 4, 5, 6. N is always going to be how many numbers do I have. So distance from the mean here, what I'm going to do is I'm going to take each x value, I'm going to subtract out the mean, and then I'm going to take the absolute value. And it's easier than it sounds. It's harder to say it than to do it. Here's my mean. So 1 minus 5. -4, but I want the absolute value. So think about what's the distance between 1 and 5? What's the distance between 3 and 5? What's the distance between 5 and 4? Distance between 5 and 6? Distance between 5 and 7? 2, distance between 5 and 9. So do I have all my distances? Once I have my distances, what do I do? Add them up and divide by 6. My n, because I'm taking the mean of all these points. You take 4 plus 2 plus 1 plus 1 plus 2 plus 4. Divide by 6. Let's see what we get here. Let's see. The top adds up to 4 plus 2 is 6. Plus 1 is 7. Plus 1 is 8. 2 is 10. That's 14 over 6. And then we are going to go to a decimal because this is more like a real life situation. So what do we get to the nearest hundredth? Okay. 2.33. So it's 2.33. That's your mean absolute deviation. On average, each point is about 2.33 units away from the mean, on average. And that's kind of telling us, you know, to me it's a small number. They're reasonably close together, and I'm looking at the numbers. They're not crazy different. My range is 8. So these numbers are not all that far apart. And that's what that's telling me. So let's do an example. Let's look on the top of page 3. Another example, I should say. We're going to do another example here. So this is, how many numbers do we have here? 4, 6, 8, 10, 12, 14. What's my n? What's my n for this? 14. You just count the numbers. So we have to find the mean. So go ahead and find the mean. I'm going to use the calculator. I still think that's the easiest way. Stat, enter. Remember how to clear it out? Up 1, clear it, and press enter. Enter all those numbers in. Because again, I do want you having practice of using the calculator. Because I know some of you are still fighting me on it. I don't want to use the calculator for this.
You don't put this in one line?
Yeah, it's all one data set, so they all go in the same list. Once you put your data in, remember what you do? Once your data's in. What do you do once the data's in? Not yet. Check it once, check it twice, right? Check your data. Make sure you have it in there right. That was a trick question. You were given the right answers. All those numbers are part of it. Yep, that's our data set. I don't know what these are. Let's pretend they're temperatures. Yes. Okay. Once they're in, remember, stat, cal, yeah. And the resistance. All right, what's my mean? My mean is 45. All right, so let's put that in. Got that. Find the distances from the mean. Okay, let's see. Got a lot of points here. So what's 45 and 10? What's the distance? What's the distance between 30 and 45? 50 and 45. 60 and 45. Oh my God, we're just subtracting, right? 70 and 45. 30 and 45. 45 and 80. 90 and 45. 20 and 45. 30 and 45. 40 and 45. I got 2 of those, right? 60 and 45. 20 and 45. I hope I didn't leave any out. Right, so I find all these distances from the mean, then what do I do? Then what am I dividing by? Oh, that's a lot of work. See if we can get it. See if we can get it.
How do you get those?
I took the 45 and I looked at the distance between 10 and 45. And I took the absolute value. It's really, technically, it's x minus the 45, so that would give me minus 35, and I took the absolute value. Right? Let's see if we can come up with a number for the minute. Yeah, what'd you get? 20. Me too. She's fast. She's really fast. But how about with that process? What do you think? Hard or not hard?
It's hard.
Once you get it, it's not that hard. Because what are we doing? Find the mean, subtract the mean from all Right, 15, 11, that's 39 away. You do that for all of them, then how do I get this? Add all these numbers together and divide by